is recommendation. So I just propose some new opportunity for future development for CCS technology in Thailand and see what will happen. So in the first topic is the climate change and carbon dioxide and how we relate it. So I know most of you might hear about the Wi-Fi in Los Angeles last week. That's quite so weird, right? So this might be one of the effect from the climate change, and this is a special report from BBC News that how severe the Los Angeles fire was. Okay, so let's see a little bit. And sorry for the advertising. Okay.
Station comes to California.
Let's get out of here.
Residents for their lives.
There's nothing we can do now, bro.
We had everything like a Sethanant. My mom passed away. We had only a few things of hers left.
All the stuff that's here is replaceable. People are not, so having family is the most important thing.
To destroy on an unprecedented scale.
People would normally be driving up and down here with surfboards on top of their cars, ready to enjoy a day at the beach. But right now, it just looks like some sort of apocalypse.
Firefighters struggle to hold back the flames.
All 29 fire departments in our county are not prepared for this type of widespread disaster.
Fires spread so quickly.
So just the brief result from the LA5. So, and if you have any want to about the detail on this report, you can Google it. And then is there any relationship between the fires and climate change? So I found the article from the New York Times said that we are in a new era, how climate change is supercharging disaster. That they said the 2024 was the hottest years in the recorded history. And wildfires are highly unusual in Southern California in January. That's supposed to be a raining season. And also from article from CNN Climate said that the LA5 were the largest and more intense because of the warming pollutions that the researcher at the University of Los Angeles say that we can blame the climate change about 25% to make the fires more intense. And of course, the research have to be more conducted in the future. And is there any relationship between temperature and carbon dioxide from the right panel? You can see the plot from 1880 to 2021. And the y-axis is the temperature increments that based on the early industrial baselines. So you can see the increasement and well correlation between temperature and carbon dioxide and exponentially growth in the later years. So it's quite well correlated, right? And the right panel is the storm intensity. So let's say, so you can see the prediction in the future in the red area. Yeah, said that in the future we will have more fluctuations in storms and we will face more frequent and longer lasting period of the storm. Then we know that the how severe that was, and if we have any method to reduce carbon dioxide, so CCUS technology is one critical tool to reduction to reduce carbon dioxide. And this schematic model from IEA showing that CCUS is more intense and more important in the future. Of course, we don't say about 3 year or 5 year, but how about like 20 years later, and the CCUS technology will have a more contribution on the carbon dioxide emission reduction. So some of you might very well know about CCUS technology, and some of you might not familiar with it. So it is simple, it's just 4 steps here, and you have 2 options. So the first step is capture, where carbon dioxide captured at the power plant or industrial factory or even from the air. So we call direct air capture. Then the captured carbon dioxide will be transported by pipeline, ship, or a truck. And then you have 2 options from A, B to C, which is the storage. So we store carbon dioxide permanently in the geological formation. And you have the other option is A, B, and D utilization. So we use the carbon dioxide as the initial substance for produce feedstock like chemical product, fire distinguisher, or urea, the fertilizer, for example. So how the CCUS technology play an important role, because this technology can reduce carbon dioxide from an existing source like power plants or cement industry, and also still the only technology that can significantly reduce carbon dioxide from heavy mineral. That's quite hardly to reduce like in cement factory or steel or petrochemical. And of course, supports hydrogen production that will have more demands in the future. But for the geoscience part that we are relating to, so I will talk just only the carbon capture storage and A or B and C part, okay? So you may have the question that how carbon dioxide capture all around the world, and is it this technology accepted? So from the world at large here, you can see the gray spot where the carbon dioxide source is located, and you have the CCS project in the different stage of development. So the yellow one represents the project that in the feasibility process, and light green is the EPC or engineering, procurement, and construction process. And the green one that we want is the operation project that are existing nowadays. And we also have some projects that are inactive and hold status, okay? Then that's all about the first part. Okay, then we will move to the main part of our talk today is the geological carbon storage. So I will talk about 2 options, CCS or carbon capture and storage, and mineral carbonation, the brand new technology, and of course, the case study for each particular method. So we have any options, so how many options that we have to store carbon dioxide in the geological formation? So nowadays we have like 6 options here. The first one is depleted. We can inject in the depleted oil and gas reservoir, where the reservoir is no longer have any potential of oil and gas. Or number 2, we can use the carbon dioxide to inject in the reservoir that can push the oil into a production well. Or number 3, we can store it in the unused saline aquifers. Or even number 4, we can store it in the deep unmarable coal seam that, as you know, the coal is high permeability and permeability that can absorb the carbon dioxide. And the last one is the in situ mineral carbonation, where we store carbon dioxide in mafic and ultramafic rock, for example, basalt in this case. So today, I will talk about the number 3, the deep saline aquifer, that will bring the example to discuss with you, and the number 6, the in situ mineral carbonation. But before we go through the example, we just have to understand a little bit about the basic concept of CCS and how we can store it beneath our feet. So basically, we inject carbon dioxide and stores in geological formation as supercritical fluid. So to reach this condition, we have to store the carbon dioxide beneath the Earth's surface more than 800 meters that carbon dioxide can keep as the fluid safely. Otherwise, it can become gas and leakage to the surface. So what happened after we inject carbon dioxide into the geological formation? So the carbon dioxide is trapped in the different mechanics. Some of carbon dioxide can be trapped in structural or stratigraphic trapping, whether the anticry, stratigraphic pinch out, or lateral phase change, for example. And some is trapped as a residual carbon dioxide trapping, where carbon dioxide tap between the pore space of the sandstone. And some is dissolved in the formation water, so we call the solubility tapping. And the last one, some of carbon dioxide turn to mineral, the carbonate mineral that we call mineral tapping. This one that we want because the carbon dioxide turn to the mineral, so it is a stable form that have a low risk of leakage. However, it's quite requires a longer time, about like 1,000 years, for example. And before the examples, I would like to introduce the phase of CCS project from start to the end of the project. So we have 6 important steps here. And the first step is the resource assessment, where the geoscience, with the geology and geophysics play a critical role to select the right location to store carbon dioxide. And of course, we have to do not only the storage assessment, but also the source assessment, the location where the carbon dioxide located and how far is it. So it's not just only the geology, but techno-economic as well. And then we have the main phase, 3 phase. The site development, construction, and operation phase, where the project is injecting carbon dioxide into the geologic formation. And along with this process, we have to do the MMV, that stands for the measurement, monitoring, and verification, to ensure that carbon dioxide is in place and no longer leak to the surface. And then after the project ends, so we close the well and we do the decommissioning, and we still have to monitor how carbon dioxide behave in the geological formations, just to ensure that it is still safe of the carbon dioxide down there. Okay, so this is a case study. I mean, one of the best case in the world, the successful case to store carbon dioxide in saline aquifers in southwest Norway. So this called the Sliner project. So this project is an offshore CCS project, about 250 kilometers from the coastline. But the first stage, this project is the petroleum production. The type is gas and condensate. However, the characteristic of the gas and condensate is high carbon dioxide contains about 4 to 9%. That exceeds the specification that allows only 2.5%. So they have to remove the exceeded carbon dioxide and inject to the upper formation. It's called Ursula formation since 1996. Today, this project still operating, and we have the cumulative amounts of carbon dioxide, 25 million tons nowadays. So the project is located here offshore Norway. And this shows you the schematic models of the project. So first, they produce condensates and gas from this formation. However, as the higher carbon dioxide content, they end up with the solution that they store carbon dioxide in this formation, Usila formations. And fortunately, they have two seal. So the upper seal is the Northland shale here to prevent the leakage of carbon dioxide, and the lower seal here. So here is the characteristic of the Usila formation, the storage formation that they inject carbon dioxide in. So it shows high porosity and high permeability as well. The thickness is about 200 meters, so it's quite thick formation, right? And in between this formation, you will have these small thin layers of mudstone that can like partially prevent migration of carbon dioxide. Okay, following these schematic models. And again, I would say, fortunately, this storage formation, the clean sand Usila formation, is a well distributed in this offshore Norway, and also the upper seal is also well distributed. So this is a good factor for the saline aquifer, that they are thick and well distributed. Okay. So here is the model of injection. So this is the injection point where they inject carbon dioxide as a supercritical fluid, and then the plume of carbon dioxide migrates to the upper layer. And you can see this the simulation. So finally, it's end up with 9 sub layer for stacking carbon dioxide. And you can also see in the lower part here the 4D seismic monitoring section that they conduct seismic from 1994 to 2002, showing the progress of carbon dioxide injection. Yeah, so the blind spot indicate the carbon dioxide that stored it in the sandstone formation. And they also conduct the MMV, the measurement, monitoring, and verification that I mentioned earlier, that to ensure the carbon dioxide is still safe in the formation. So they did many methods like control source, electromagnetic surveys, seismic survey, gravity survey, and C4 mappings, just to monitor the location here. And this is a result of the 4D seismic from 1999 to 2008, that you can see the expansion of the carbon dioxide plume in the north-northwest, south-southeast direction here. And this is a seismic conduct in 1994, show the baseline before the injection of carbon dioxide. And this is the post-injection in 2008, where you can see the bright layer of carbon dioxide here. And here is the difference, okay, from these two timelines. And also the results of gravity surveys across the storage location. So they put the gravity meters on the sea floor and do the test. So you can see the low gravity as a result of low density of carbon dioxide here at the plume of the carbon dioxide. This is one of the methods that they use to monitor the carbon dioxide migration. And that is the first study example for carbon capture and storage. Then I would like to share the new technology that interested today, which is in situ mineral carbonation, where we inject carbon dioxide in the basaltic, like mafic and ultramafic. So let's see what happened here. Basically, they mix carbon dioxide into the water. And then after mixing, so as you know, it forms carbonic acid. And then the carbonic acid is not stable, right? So it become bicarbonate and hydrogen and the carbonate part here. So after that, the acid water break down the silicate mineral like olivine. So for example, in this is like big Mg apart. And then this Mg bond with the carbonate. So it become the carbonate mineral. So in this case, MgCO3. the magnesite here. So why this method is interesting, because it doesn't request the cap lock as compared with the conventional CCS, because carbon dioxide and water is already mixed in on the surface. So the solubility trapping should occur immediately, right? And over time, this solution become carbonate mineral faster than the conventional CCS. So you can see here the figure comparison between conventional CCS and mineral carbonation, showing that in the x-axis here. So it required like 100 year or 1,000 year before it form mineral tapping in conventional CCS. But how about the mineral carbonation? Just only 1 year or 2 year, you have like 50% that solution become mineral and form as a carbonate mineral, whether calcite, siderite, or magnesite. So this is the pilot project located in the Southwest Iceland. The source of carbon dioxide come from this spot, the geothermal power plant, and they transport the carbon dioxide along the pipeline until this location, the injection location. And of course, you have require fresh water from this well. So it meet here. And this is the injection location where they inject carbon dioxide into the basaltic rock, in this case, that deep, that have depth about the 500 meter down there. So this is a cross section along the study area. So you have two rock units here. The first one is the storage formation, that basaltic lava flow here, the blue formation. And you have hyaloclastite that defined as the confined layer, even though we don't request the upper layer to block the carbon dioxide migration, but still we have a good formation just to cap the carbon dioxide here, even though we actually don't need it, but right, have it to ensure it. However, even though that the mineral carbonation technology is quite interesting, but still we are in the research and development phase, as the technology readiness level is about 2 to 5. So it's not yet commercial compared with the conventional CCS that I talked earlier. At the is in the stage 9 or commercial and continuous use, whether the inject in saline aquifer or EOR or enhanced oil recovery. So more research and more pilot project need to be conducted. Okay. So here is the results after injection in vesicular basalt. So in this case, you can see the calcite precipitated in the pore of the basalt in the lower left picture as well. However, you can notice that some of pore is not filled by the calcite, because that pore is not connected to the other pore. So usable pore can be seen only the connected porosity, or you call effective porosity, right? Yeah, in the blue color, and they simulate the network of the pore space. So only some of the pore can be used to store carbon dioxide. It's quite challenging about the heterogeneity of basalt out there if we don't have much information that the characteristic of the basalt. And last one, I would like to address about the recommendation of Thailand and any future development for Thailand, as today, as you know, Thailand have national subcommittee on greenhouse gas reduction using carbon capture, utilization, and storage technology. And as you know as well, that now we have net carbon dioxide emission, greenhouse gas emission, sorry, about 280 megaton carbon dioxide equivalent that still increasingly more in the future, is about 2% per year, right? And where is the CCS and CCU technology in Thailand development? So this technology is assigned in the Thailand greenhouse gas emission development strategy. The official paper that we submitted to UNFCCC said that Thailand will adopt this technology in 2040 for both power generation and also in cement industry. So that's why we have to prepare ourselves, prepare our personal, our knowledge to at least evaluate the site whether it's is suitable or not for Thailand. But we can say that confidently Thailand is ready for this technology or not. The early research that I searched in Google showing that there are carbon dioxide source in Thailand that concentrate in the central part of Thailand and also in the eastern part, as you know, the Eastern Economic Corridor or EEC, at the different industrial sector here. And also the right picture show the carbon dioxide emission from fossil fuel power plants as well. So this is the Memok power plant in Lampang, and of course from center part of Thailand and Sratburi, where's the power plant located in the EEC part here. So for the offshore, PTT group has an initiative which is Eastern Thailand Carbon Capture and Storage Hub initiative that industry in PTT group will collect carbon dioxide and stores in the offshore Thailand here. And another pilot project that I hope it will happen very soon is in Atit gas field in the Gulf of Thailand. So they capture carbon dioxide from production well and inject into the saline aquifers and depleted reservoirs like the Sliner project that I mentioned earlier here. But you also see that they are still have many carbon dioxide spots in the central part of Thailand and some in the northeast part. And how about the potential for the onshore storage? So Thanasak Suktavi and his colleague did this paper published in International Journal of Greenhouse Gas entitled Accessing the Geological Storage Capacity of Carbon Dioxide in Korat Sandstone, Geochemistry and Fluid Examination. So basically they collect sandstone in Pupan Formation in Korat group as the outcrop, okay, here from the sandstone mining. And then they put this core sample into this machine called carbon dioxide flooding machine. So basically they try to simulate the environment and how carbon dioxide behave after injected in the core sample. So in the first state, the original one, so this is the picture of the pore network of the core sample showing the porosity here. So there is nothing inject in this state yet. And the B state where the carbon dioxide and blies injected in this state. And you can see the porosity dramatically decrease as the solution of lye and carbon dioxide fill in the pore. And the last state where they inject supercritical carbon dioxide. So you can see the slightly increase of the porosity and permeability here because of the small fracture formed and also the dissolution of quartz grain that results in a little bit increase of porosity and permeability. Okay. So here is a graph from the experiment. So this graph plot between carbon dioxide saturation in x-axis and relative permeability in y-axis. So we have two states here. The first state is they call drainage state, where the state that they inject whether brine or carbon dioxide. So the injection state. And then you have the second state is called imbibition state, where they stop injecting carbon dioxide or brines and leave it to let the sample stable and see the results. So to ensure that our experiment is get along with the international model, so they use the Korea model as the international benchmark to see the correlation between the experiments and the international benchmarks. So fortunately, you can see that the experiment and the benchmark is quite well correlated. So here at the starting point, after you inject carbon dioxide, so the carbon dioxide saturation is gradually increased until it reached this point where they cannot inject carbon dioxide anymore. So they stop the injection. And after that, some carbon dioxide released from the pore and then back to the stable phase. So finally, we can say that residual carbon dioxide that is trapped in the pore is about 2.26%. So it's about 0.26. So it means 26% of the pore volume can be filled of the carbon dioxide. So this number is quite a good number because it falls in the range of international range that ranged from 0.01 to 0.52 here. So even though this experiment use the outcrop sandstone, that it actually should be the sandstone from the geological formation that we give the suitable environment. However, we can see that in the early stage of the research, the Phupan sandstone can be used as a potential storage formation for the onshore geological storage in Thailand. And of course, more research must be conducted to ensure that this will suitable. Okay. And for the mineral carbonation in the northern part, here as we know, we have the carbon dioxide spot in the Memo power plant. And fortunately, we have basalt flows in Meta basalt, it's located here. So you can see it's vesicular. It is vesicular, but it is not homogeneous because some location might have a pore, some is a solid basalt. So yes, it might be good if we have more research on this rock unit to use as the mineral carbonation storage formation in the future. Okay. And so this is the end of my talk. And of course, if you have anything to add on or any comment, is highly valuable to support and to drive the CCS implementation for Thailand. Okay, thank you very much. ครับ
Thank you, Khun Nattaphan. And is there any question or comment? Please feel free to share your opinion. And now the floor is open for you all. If you feel more comfortable to speak in Thai, you can. ช่วงถามตอบแล้วค่ะหรือมีข้อเสนอแนะความคิดเห็นแชร์กันได้เลยนะคะมาแล้วคำถามแรกค่ะสุภวิทย์จากคุณสุภวิทย์นะคะ In your opinion, what is the most promising option for the carbon dioxide storage, considering various geological media. For example, depleted oil and gas reservoirs, limestone, caverns, or etc.
Okay, to answer the first question first, I have to back to this figure here. So depleted oil and gas reservoir and the saline aquifer have pro and con for its own. The advantage of depleted oil and gas reservoir is the information that we already know because we did the survey before we produce petroleum from that location. So you have well information about the characteristic of the formation there. Okay, the porosity, permeability, chemical alterations, right? So this is the good news for the depleted oil and gas reservoir. The bad news is this reservoir might have located in the deep. So at that point, you have more pressure in that reservoirs. And move to the saline aquifer. Normally, the good news is, as I say, it is high distribution and thick layer, so it can store carbon dioxide more, okay, commonly compared with the depleted oil and gas reservoir. But the con is, we have to do a new research, new survey to see what is the behavior of the saline aquifer that distributed in the area that we are interested. So right, we have to do more research on that. Okay. I'm not sure I cover or not the question.
Yes, and for the second question is to ensure that carbon dioxide doesn't leak and remains securely stored. Are there any cases where AI is being used to improve the monitoring of storage size or in other applications?
Okay, I hope so. There are many discussion how we can monitor effectively, because once we did the survey, it means the cost that we have to pay just to ensure the carbon dioxide is still in place, and there is no return for that survey. And nowadays, I would say to you, there are many research on the geophysical to monitor carbon dioxide in the storage reservoirs. Some like they use the what they call is the fibers that can install it in the sea floor, and then they detect the vibration, so it can respond to the leakage of carbon dioxide. So once they receive the signal from and the underground surface, so this signal can be processed and can be used to monitor carbon dioxide effectively, rather than we did the seismic survey that cost you very much. And thank you.
And the next from the Kun Sasin. Thank you for your presentation. From your presentation, you show the Bhutan formation was effectiveness of the carbon storage via porous. Hence, I would like to ask that is possible to make CCS station at the northern or northeastern part of Thailand.
Okay, thank you for this question. Okay, to answer the question here, I'll back to this figure. So you can see here the source location of carbon dioxide here, right? In the central part, for example, Saraburi, which have power plants and cement factory there. And for the distant aspect between this one to the offshore Thailand is quite longer than if we can transport the carbon dioxide from here to the northeast part of Thailand. The condition that we have to research more is where the Phupan located beneath more than 800 meters down there. So the survey must be conduct like seismic survey just to locate where's the location of the Phupan sandstone in the Korat Plateau. Okay, and then of course for the surface as well, the area that can be have the permission to access for the site construction as well. So I would say yes, we have the potential for the northeast part of Thailand where the Phupan sandstone located beneath 800 meters and can be used as a storage location for the carbon dioxide from the central part of Thailand. Okay, thank you.
Thank you, Nattaphan. And any preliminary study about mineral carbonation potential site in Thailand? And thank you for your sharing knowledge.
Okay. As I know and as I mentioned you earlier that mineral carbonation is quite a break in Thailand. I'm not sure that now is there any research institution to conduct a research of the suitability of basalt in Thailand that can be used for the storage carbon dioxide. So from my limited knowledge, I don't know yet. Okay, thank you.
จากคุณทรงกฎค่ะ ถ้ำถือว่าเป็น carbon dioxide potential source ไหมครับ
ครับผมคิดว่าไอ้ตัวถ้ำนะครับคือตอนนี้ครับในถ้ำเนี่ยอาจจะไม่เป็นคาร์บอนไดออกไซด์โซร์สนะครับแต่ว่าเราอาจจะใช้ถ้ำเนี่ยเป็นตัวดูดจับคาร์บอนไดออกไซด์จริงๆเป็นปรากฏการณ์ธรรมชาติที่ถ้ำเป็นอยู่แล้วนะครับก็คือว่าคาร์บอนไดออกไซด์ในบรรยากาศที่อยู่ในถ้ำเนี่ยครับจะไปทำปฏิกิริยากับไอตัวน้ำที่อยู่ในถ้ำนะครับดังนั้นคาร์บอนไดออกไซด์อากาศนะครับไปเจอกับน้ำที่อยู่ในถ้ำเนี่ยแล้วก็จะเกิดเป็นกรดคาร์บอนิกใช่ไหมครับดังนั้นเนี่ยตัวกรดคาร์บอนิกเนี่ยก็จะไปละลายในตัวไลม์สโตนที่อยู่ในถ้ำนะครับซึ่งก็ตัวไลม์สโตนตัวนั้นนะครับก็จะไปรวมกับไอตัวคาร์บอเนตในไลม์สโตนนะก็จะไปรวมกับคาร์บอนไดออกไซด์ที่ถูกตรึงมาจากในอากาศทำให้ฟอร์มเป็นอย่างพวกทูฟ่าทาวเวอร์ทีนอย่างเงี้ยครับซึ่งก็จะสามารถใช้ได้เนี่ยเป็นตัวที่จะดูดจับแต่ว่าคืออย่างไรก็ตามเนี่ยไอตัวการดูดจับของคาร์บอนไดออกไซด์ในถ้ำเนี่ยคือทางประเทศจีนนะเขาก็ศึกษากันแล้วก็ทำกันอยู่นะครับเพียงแต่ว่ากระบวนการที่เราจะไปคำนวณนะครับความสามารถของถ้ำเนี่ยว่าจะสามารถดูดซับคาร์บอนไดออกไซด์ได้เท่าไหร่เนี่ยน่าจะเป็นสิ่งที่ยังต้องทำรีเสิร์ชต่อไปนะครับขอบคุณครับ
Hi, I have a quick question. For the basaltic formation, what do you think of in terms of the size of the formation would be required in order to store enough carbon dioxide for Thailand, for example? And with that suggested size of the formation, will the example that you brought up in memo case be efficient to be stored to store the carbon?
Thank you for the question. I would say before we assess, we did before we do the evaluation of the storage. So we must evaluate the source, how much carbon dioxide released from the source, right? And then, as I say, that this mineral carbonation is still in the pilot project. So, for the size of carbon dioxide, for the size of basalt, let's say in this case, it's actually we have to calculate the pore space in basalt, that the potential of the pore space, how much the pore volume inside the basalt. So it's quite have to do very more research details on this. So I cannot answer your question yet, honestly. And for this, there are many controversial on this, because as I mentioned, the heterogeneity of basalts. So not all basalt is porous, right? So like we have 3 sections of basalt: the columnar basalt, the lower one, the middle one, then the flows in the upper one. So not all layer of basalt is porous. So the more core calculation must be conducted just to calculate how much the storage we can store. Okay, thank you.
So what kind of depth that we need for the formation to be?
Okay, for the depth of basalt, theoretically, we don't need that depth, because basalt, because the carbon dioxide and water already mixed together and form as the solution. So as the carbon dioxide is not in gas stage, but in the solution state, so the leakage of the carbon dioxide is very, very low compared with the conventional CCS that they inject the carbon dioxide as supercritical fluid. If the fluid leakage at the certain depth below the 800 meter, like 500 meters, say, so it's become gas and easier to release to the surface. Okay, but I think practically in the Kalfik pilot project in Iceland, they still do the like double protection, let's say, to inject carbon dioxide in this depth, this layer. So the depth is about 400 to 900 meter.
I think the temperatures also plays a very crucial role in exchanging, I mean, the position of the carbonates within it. So it seems to be there's a lot of parameters that you have to think about, and
Right.
I think there'll be a lot of space for studying these concepts, especially in Thailand. We still really have to study a lot. And I don't know what's going to happen in the future, whether in which direction that we are going to head for. Like I mentioned earlier about the Trump's administration's direction. It seems to be back and forth between the climate change and petroleum exploration. And so I don't know, it might be a question about whether this kind of project is going to go ahead, or is there any holdback on this to, you know, slow down the progress of study? I don't know. It depends on the national policy and the source of funding that you are going to get, right?
Right.
Okay. Yeah,
And
thank you.
I think I would like to add more about the US situation. I think for the US, they Trump policy is like shift from the climate change reduction, right? But still, I think the intensive for support CCS technology is still there. So I think they say they can use more petroleum or whatever, but they just want to develop a new technology to reduce carbon dioxide instead of stop that technology. So like roughly they said they don't care how much carbon dioxide released, but how much carbon dioxide can be stored using new technology, I think, for the US.
I believe that your background is from the energy sector, right?
No, it's in geophysics.
You've been using, you used to work in any kind of petroleum?
No,
No?
sir.
Okay.
Okay.
But anyway, from my quick point of view, Trump's administration, they just want to secure energy for their country's development, which is totally a different perspective and compared to the climate change. So we have to think about it carefully and we have to analyze it, what's going to happen according to the direction that he proposed. Yeah. Okay.
Thank you very much for your
Thank you.
comments. Thank you.
Yes. Due to overtime, I think it's that enough for the first presentation. Thank you very much for all question, comment, and information sharing. And the next speaker was also very interesting, and I was quite excited because her was very experienced with the exercise in the earthquakes and the use of a geographic information program. Welcome, Dr. Israporn Sethanant. Let me introduce about Dr. Israporn. She is a research fellow in earthquake science at the University of Melbourne, specializing in the ground displacement forecasting for the reducing disaster risk in the South Australia. She holds the PhD in the Earth and Ocean Science from the University of Victoria, Canada, with a dissertation on using InSAR to discover and characterize earthquakes on the immature faults. Her academic journey is include the Master in the Geology from Oregon State University, USA, and a Bachelor's in Geology from Chulalongkorn University, Thailand. Her work includes significant publications on seismic hazards, fault systems, and earthquake behavior, along with the experience in paleoseismic trenching, fault mapping, and remote sensing. Dr. Israporn has delivered numerous conference presentations and received prestigious awards, including the Seismological Society of America Student Presentation Award. She is also deeply involved in teaching leadership and community outreach, promoting earthquake science through the innovative methods and public engagement. Please welcome Dr. Israporn Sethanant for the presentation on applying InSAR to map hidden faults in Southeast Asia.
Thank you so much for this warm welcome at DMR today. I'm really honored to be here. And again, I'm also, please feel free to interrupt me for those in the room or also for folks in Zoom if you'd like me to explain some certain concepts in between my presentation. So I'd like to start with a scenario actually. I'm going to invite everyone to imagine with me if this crack in the ground that is generated by this earthquake in the United States in 2020, it ruptured on a fault that has not been mapped before. But if we fast forward around 10 or hundreds or thousands of years, imagine that the dust will fill in these cracks, maybe an alluvial fan would there's a flash flood that covers this crack, and now you don't see this fault anymore. And then you were given this land to build a beautiful house where you oversee the mountains in the back. But the question is, where are you going to choose to build a house if you don't see the fault? So the importance of earthquake studies is that our building codes and all of how we construct our communities is based on the knowledge of where the faults are. But the problem is there are damaging earthquakes that occurs on faults that we do not see. So throughout my PhD, I investigated earthquakes that ruptured on immature, hidden faults. I found that there are some common rupture behaviors that we can observe from these type of earthquakes. And I hope that by the end of this story, I will have convinced you that even though these earthquakes are difficult to study, but with the right tools and the combination of different tools, we can actually take away some key information to improve the seismic hazards of our community. But first of all, what exactly is immature or the hidden faults that I have in my title? So structural immaturity is the concept, is a term that describes the evolution of fault through time. So a fault that has hosted a lot of earthquakes, accumulated a lot of earthquakes, is more mature, and faults that hosted fewer earthquakes are immature. What does that mean on the surface that we see in the ground is that when we look at this earthquake that occurred on a fault that has not been mapped before, when we compare it with the famous San Andreas fault, you can see this pronounced lineation in the topography. And the San Andreas fault is known to have hosted a lot of earthquakes through thousands of years. And so we can draw this lineation on the map very easily. We know that a lot of earthquakes around the world in the past few years is a great example that the San Andreas fault style or Sakai fault in Myanmar is not the only type of earthquakes that can be very damaging. And one of a great example is the 2020 Pentrina earthquake in Croatia. It caused serious destruction. And when we look at the map of where the earthquake epicenter occurred, the red line is showing the fault that this earthquake ruptured, and it has not been mapped before. And I am showing this example because it highlights the key advantages of InSAR. How can InSAR help us learn more about these earthquakes? I'm going to overlay InSAR on top of this topographic map, and these beautiful, beautiful cycles of colors, I think it's beautiful. All these colors that you can see are the deformation that is caused by the earthquake. So the first advantage of InSAR is that even though the earthquake does not come up to the surface, InSAR can help us identify where is the main fault trace. Number two, another advantage of InSAR is that because it has a high spatial resolution, we can communicate to emergency responders, communicate to firefighters, where is the deformation area that we should expect this earthquake to cover. We can send help to the local communities, to villagers that need help. And the other crucial information that we can get from InSAR is that sometimes the nodal plane of a focal mechanism has two possible nodal planes. But then with InSAR, we can actually discern or actually point out which one is the primary nodal plane. So now that we have this powerful InSAR tool that makes it possible for us to study earthquakes on immature or hidden faults, I would like to walk you through this journey and invite you to have this question in the back of our mind throughout this presentation. What are the rupture behaviors that we can learn, that we can see from earthquakes on these types of faults? And by knowing that, what is it that we can use to improve the seismic hazard models, especially the case study that I'm going to show here is in Southeast Asia, or in Thailand and Laos and Myanmar to be specific. So the tools that we're using is mostly InSAR. And in my PhD, I have also produced the InSAR lookbook, and I'll introduce to you what that is. And I'm going to apply that to the 2019 magnitude 6.2 Sayabuli earthquake in Laos. So before we get into all the details, it's important for us to understand what exactly is InSAR. So InSAR stands for Interferometric Synthetic Aperture Radar. It's a differencing technique between, we have two InSAR images before and after an earthquake, and we create that difference between two images. This is a cartoon topography I'm showing, and the long arrow is where the satellite is orbiting. And it is important to note that the satellite is looking actually across the track. So here's a cartoon satellite orbiting. It's sending out microwave signals, and what it measures is the amplitude of backscattered energy and the phase. Now, when an earthquake happens, the ground shakes a little bit. The satellite orbits approximately the same location, but now the phase that is returned back to the satellite includes the phase shift because of the ground motion of the earthquake. So this phase information is displayed in the format of fringes. So I don't want you to feel shocked to see all these colors. Allow me to walk you through. So the phase that we just saw earlier are now overlay on the topography. The order, and it's the contour of surface displacement. So if you see more fringes, there is more deformation. The order of the color from red, yellow to blue, or blue, yellow to red, means that the ground is moving towards or away from the satellite viewing geometry. So remember, this cross arrow is very important because all the deformation now is relative to the direction of where the satellite is looking. And how normally a satellite, how it works is that the ascending track is where the satellite travels from the south to the north. So from the south to the north here, it's looking to the right and down. In the descending track, it's traveling from the north to the south, so this arrow here, and it's also looking to the right and down. And so these two geometries of the satellite will tell us about how the earthquake happens and what is the fault geometry that produces the fringes. So let's look at some real world examples. I'm showing the 2022 Mandarin earthquake in China as an example. And again, this is an ascending satellite and we're looking to the right. So just a reminder, now let's take a look at where the color changed from red, yellow to blue. So if we look at the north here, the color in the fringes are changing from red to yellow to blue. And again, red, yellow to blue, red, yellow to blue, moving inwards towards the signal. And that's how we know that the northern lobe is moving towards the satellite. Now, when we look at the southern lobe, here, the color is changing, starting from the outer of the image towards the inner. It's changing from blue to yellow to red, blue to yellow to red, all the way in. So we know that the southern lobe is moving away from the satellite viewing geometry. So when we combine the relative displacement between the two lobes, we are able to infer that this earthquake occurred on a northwest trending left lateral strike slip fault. To confirm that this interpretation is right, we will take a look at what the signal is like in a descending interferogram. So now the satellite is traveling from the north to the south and looking to the side. Again, with the order of the color cycles, the southern lobe is moving towards the satellite, the northern lobe is moving away from the satellite. And this confirms our interpretation of the left lateral strike slip fault. And this is how we usually use InSAR to help us infer what the source of the earthquake is. However, there is some gap of understanding of how to read InSAR. So a lot of times when large earthquake happens, there are a lot of interferograms that are shared in Twitter, in a lot of the media platform. Even some signals, InSAR specialists have difficulties in understanding what the signal means. So me and my colleagues, we generated this InSAR lookbook. So basically it's an atlas of static interferograms. Oh, I forgot to mention, interferograms is the result image after we do the differencing between the two images of InSAR. So the InSAR lookbook is a static interferogram that Again, here there's a lot of panels. Allow me to walk you through. So all of these two panels here are the ascending and descending pairs of interferograms. And the black line in the middle is the 20-kilometer long modeled fault. The orientation of the satellite stays the same, but what does the signal look like if we change the strike for every 30 degrees increment? This InSAR lookbook will have these sets of interferograms for 10 different faulting striles. When we look closely at how the signal looks like, when the earthquake is rupturing and north striking, there are mainly two lobes of InSAR, and then the signal starts to distort as it moves to an east-west striking fault. So it's quite complicated. And just to simplify things, you can actually think of this as a snowman. So a lot of times when it's a dip slip faulting, you'll usually see 2 or 3 lobes of InSAR. So imagine this would be the bottom, the center of the snowman, and the head of the snowman. When it becomes a more complicated east-west striking fault, you can actually think of it as a balloon model animal. So this is one of the kind of diagnostic features that we can see in a north-south and an east-west striking fault. We're having 2 snowmans opposite side and this balloon animal on the opposite side. Now that if we have a large earthquake, if you see interferograms published or posted in other social media, you can utilize this lookbook and then compare the sets of interferograms with this lookbook to actually say that, oh, it's a north-south normal fault striking at around 25 degrees, for example. So we're going to do a little exercise together. I'm going to show a few of the applications that we can use the lookbook. I'm having these left lateral strike slip lookbook on the right-hand side, and the ascending interferogram of the Melbourne earthquake and the descending interferogram of the same earthquake on the bottom. I've actually given out the answer, but I would invite you to look through this clock and see if, would you agree that the signal of these two is matching what I have put a box around? I will pause for a few seconds for you to swath through this figure. Do you agree? สวัสดีค่ะอาจารย์
Wadija. Very good presentation. But what I'm going to ask is that this is the case where the fault is vertical.
Yes.
If you have something which is angle, maybe
Yes.
it's more complicated, I guess.
Yes.
Okay.
That's totally correct. The model here, the model that I generate is an assumption of a vertical fault. And so the way that we use the lookbook is that we need interpolation and extrapolation sometimes. So the lookbook, I want to emphasize that the lookbook is not to replace any detailed modeling. It's only to provide first order observations for people that want to be able to read the interferogram right away and get the strike dip rate, just an approximation. So I hope everyone agrees to me that these two signals fall in between around 90 or 120 strike. So there's a butterfly shape for the ascending and another butterfly shape on the descending. So I'm reading these value out of the model. So I'm guessing it's around 105 degree strike. In this model of the lookbook, I assume a vertical fault plane. So it's 90 degree and the rake is 0 degree rake. In some more detailed modelings done by Lee and others in 2022, their high resolution inversion model produces very similar results to the InSAR lookbook. But this is also because this earthquake might have ruptured a simple fault plane. But there's another application that I want to highlight is that this is again the left lateral strike slip from the lookbook. On the left-hand side are the signals from the Merkab earthquake in Tajikistan. And from the focal mechanisms, you can see that there are two possible nodal planes. And sometimes it can be very challenging to actually define, is it a northwest trending or a northeast trending fault that is responsible for this earthquake? In this slide, I don't have the red box. Yay. So I'm going to pause. I'm going to pause for a few seconds again. I'm going to invite everyone in the room and in the Zoom room to compare these two signals with the lookbook I have up here. And let's see what you got.
I have a quick question.
Yes.
Looking at this diagram,
Mhm.
I have no problem at all on these site diagrams, either on the right hand or on the left hand side. But my question would be on this strike equals 0 degrees and 180 degrees. Why the butterfly shape showing the direction of the fault in an east-west direction instead of north-south direction?
You mean this signal here?
Yeah, yeah. Is this a trick that you have to be aware of in interpretation? Because if
yeah,
you look at on the side, right?
Mhm.
If you have like say 60 degrees on your right hand side, it seems to be very clear that you have
Yeah.
a straight line parallel to the 60 degrees. But if you look at this north-south direction,
Mhm.
it turned out to be in 90 or 270
this.
degrees. Can you explain that?
Yeah, it has to do with the deformation field. Like all of these, how these signals are formed is a addition combination of what the horizontal displacement and the vertical displacement, and then you do a trigonometry and make it transfer it to a satellite looking angle. And this is a synthetic, like a perfect condition with no decorrelation, no noise in the InSAR signal. But what would give away is that this blue color is also continue around the fault tip, and this red is continue around the fault tip. But if we look at the real example of real world examples of a north-south striking fault, it will not have there would be some noise that is surrounding the fault that projects to the surface. So that will be a hint of where the fault plane is. But to answer your question,
Yeah,
this signal will have to like go look at what the displacement field is, and that's
can
how.
you use a series of how do you call it? A series of photos. I mean,
Mhm.
as a result of the image. Can you use a series of them and then or do something like stacking? I don't know. I'm using the word stacking.
Yeah.
Stacking is mean repeatedly collecting the data and then calculate it. Is this? I don't know, because usually for all geologists, right, who are not really expert in InSAR or geophysics, they would interpret the data
the other way, right?
according to the visual
Mhm.
interpretation, not really understanding
Yeah.
what kind of data they have to be aware of.
Mhm.
This is one of the problems with the geologist, basically.
Mhm.
So he or she has to have a bit of background of the InSAR technique before they can overcome this visual faults or something.
But I think that's kind of actually the motivation for this lookbook, because you're exactly right. This signal on the east-west here, it's what's tricking a lot of people to interpret that that's the fault. And that's the purpose of this lookbook, because this lookbook will tell us that if you see a four lobe, like a clover leaf, like a four lobe like this, it's an indicator of a north-south striking fault. But if you see a butterfly shape with no like swelling in the middle, if you see like this almost mirrored image of butterfly shape, it's an indicator of an east-west striking fault.
Yeah, of course, yes. If you take a look at the one at the 90 degrees, and you take a look at the one at the 0 degrees, you actually flip. It's like a mirror,
Yeah,
right?
but it's rotated.
Right, but the rotation is totally different.
Yep.
So this is very tricky. I mean, for general geologists, I think. I don't know whether the audience are with me or not. Are you aware of the figures in the 0 degrees for two of them, and the two of them in the 90 degrees? The picture of the 90 degree on the right-hand side is actually the mirror image of the 0 degrees on the left-hand side. Right?
I see what you mean.
But the direction is totally different. It's like 90 degrees different. That's one of the problems. And if you keep looking at the 180 degrees and 270 degrees,
oh, this is the same.
you might see something similar, right? Okay, that's just my observation.
Yeah. One of the things that can also help is how there is a distinct denser fringe on the west side of the fault compared to on the east side of the fault. That can help.
Actually, in terms of azimuth, right? I mean, direction, we only have 0 to 90, all right? But geologically speaking, if we have the right-hand rules of strike and dip, of course, we need 360 degrees. But if for these diagrams, if you take a look at 0 to 90 degrees, you almost have the complete picture. It's just a matter of mirror image of the 4 quadrants, right? Okay, thank you.
So for this earthquake, my interpretation of the fault source for this earthquake is a northeast striking one. And there are some hints in the data is that these small lobes in the ascending is represented in the model, and the decorrelation, or how there are more patches of inconsistency along the northeast striking trend hints us that's where the fault is rather than the northwest striking one. So with this tool, most of the times InSAR can help us distinguish what is the primary nodal plane when we already have the focal mechanisms, but we don't know which one is the causative fault. So now that we've done a few exercises and discussed about the lookbook, there are limitations, of course, and we're going to take a look at if we can actually apply this to a case study in 2019 in Sayabuli in Laos. So this earthquake ruptured in 2019 in November, and I'm taking you here to Luang Prabang city in Laos. And the earthquake ruptured just 90 kilometers away from this beautiful city, and it is also registered as a UNESCO World Heritage Site since 1995 because of the cultural heritage and a lot of history in this area. And the earthquake epicenter is only around 30 kilometers away from Sayabuli Hydroelectric Dam. So that raises a very important seismic hazard and including risk to the river communities and people living in the city. So to give an overview of the regional tectonics, the study areas in the black box on the bottom right here, which is in the Golden Triangle region, And the deformation or the faulting in this area is influenced by the collision between the Indian plate and the Eurasian plate. So these GPS vectors are showing how deformation of this collision is actually governing a lot of the slip rates or a lot of how the faults are moving in the Golden Triangle region. So zooming into the study area a bit more, Sayabuli earthquake is located where the arrow is pointing. The focal mechanisms that you see in this area, the ones that are colored are the ones that have been studied further with more detailed regional waveform modelings, including our study. But imagine if there had not been Sayabuli earthquake in this area. You can see that there is very little seismicity in the southeast region of the Golden Triangle. And without this earthquake, we will have this earthquake just provides us so much opportunity to understand what the seismic hazard could be or could be improved in this area. When we see the focal mechanisms, a lot of times because in this region, the faults that are pronounced in the topography are northeast trending left lateral strike-slip faults. So when I first saw this earthquake, I also thought that there is a high potential that it would have ruptured on the Dien Bien Phu fault, continuing to the southern extent. But now we have the tool, we have the InSAR tool. We're going to test whether this is true. So I'm going to show the InSAR signal of this earthquake in the red box with the extent of this red box here. So we have the ascending interferogram on the north and the descending interferogram on the south. We have this butterfly shape, and we have two low butterfly here. I'm also going to pull up again the InSAR lookbook and encourage everyone to swat through this image again with me and see if you would agree. What would the first order observations or the strikes, dip, and rake that we can get from the InSAR lookbook? Okay, so
How can you know this is correct?
um,
After we guess.
I'll answer that in a bit. So yeah, I've actually given out the answer because I've pulled out a right lateral strike slip lookbook out here. But to read the strike dip and rake as a first order observation, again, this is not to replace any detailed modelings out there. It's just a visual guide tool to help read interferograms. So when we have a 4 lobe in the ascending and we have a 2 lobe in the descending, it indicates that it's a left lateral trending. And then we also have to look at how the colors are changing. That's why I have given out the answer of the right lateral strike slip earthquake. When I read out this value from the model, it's striking 330 or 150 degree strike, assuming a vertical fault plane and a right lateral rake. But in order to actually get a more precise information of the source parameters of this earthquake, we did an inversion model. An inversion model is basically we're asking what are the fault parameters that is required to produce the data we see. So the column on the second column here is the model that we have embedded a rectangular fault plane. And then we did an inversion and was able to derive the parameters of this fault. So it's striking 166 degree, dipping to the southwest and striking with the right lateral strike slip fault with a little bit of a normal component. So we found that this fault does not align with any faults that has been mapped before. And it's around 20 kilometer long, and it's approximately conjugate to the Dien Bien Phu fault to the north. Now that we have this geometry, we actually want to learn more about the earthquake behavior. So we're going to project these InSAR displacement data down to the surface underneath us. So we did a distributed slip model where we take the InSAR data, we take the fault geometry that we found, and then we look at how slip is distributed at depth. So the peak slip of this earthquake, if I move here, is around 1 meter and occur around 5-kilometer depth. We can see that it's not homogeneously distributed along all of the fault planes, and all of these squares are 2-kilometer size. This model also shows us that slip is buried at depth and only a few tens of centimeters reach the surface. There's a term called shallow slip deficit that explains how slip does not fully come to the surface. And a high shallow slip deficit, or in this case, 80% shallow slip deficit is one indicator of earthquakes that rupture on immature faults. This 3D model also alludes us to the fact that in the study, we did not only do InSAR, but I draw upon collaborations to include earthquake relocation to understand this Sayabuli earthquake more. And these are relocated earthquakes that we see it is further away from the main slip plane. So we're going to take a further look of these relocated events and see, can we learn something about what the seismic hazard in the future that we can expect of this earthquake? So the image on the left-hand side is a hill-shaded topography map, and there is the Sayabuli earthquake cluster on the southeast corner. All of these circles are relocated events colored by the focal depths. So I'm also going to step out a little bit and look at this in the broader picture, not only the Sayabuli earthquake. There are other clusters such as the 2014 Melau earthquake, 2007 Bo Kaeo, 2011 Tarlay earthquake in Myanmar, and the more recent 2022 and 2023 Sieng Tung earthquake in Myanmar. So when we plot these focal depths in a histogram on the right-hand side, there is the vertical axis is depth, focal depth, and the horizontal axis is the number of events that has those depths. And we can see how the earthquakes are distributed around 5 to around 17 or 20 kilometers, which is the main concentration of where the earthquake occurs in the crustal region here. We are using the D90 as our seismically determined seismogenic thickness. So we're using the distribution of the seismicity to interpret what the layer of this region can host earthquakes. D90 basically means what is the 90th percentile that this of the seismicity in this area, and it falls in at 17 kilometer. So in this region with this relocated earthquakes, we can interpret what the seismogenic thickness could be, and engineers and seismic hazard modelers could potentially use this as a guide in future seismic hazard models. Let's take a look at the Sayabuli earthquake and see if there are other attributes that we can learn from this earthquake now that we have both InSAR and both the earthquake relocation information. Zooming in a bit more, the red line here is the InSAR, the surface projection of the InSAR fault. And you can see here that it is not projecting or aligned with any mapped faults before. On the right-hand side, we are actually plotting the histogram of the Sayabuli sequence only. So let's focus just only what the main shock is doing. So again, on the vertical axis is depth, and the horizontal is the counts. All of the aftershocks are distributed around like 5 to 15 kilometer. The dashed red line is the bottom depth of the InSAR model fault. So what we're reading from this graph is that this focal mechanism, the earthquake, initiated at 12-kilometer depth near the bottom depth of the InSAR fault, but slip propagates and peaks around 4 to 5-kilometer depth. When we combine that information with where the aftershocks are distributed, we can see that a lot of the aftershocks are distributed above the InSAR model fault plane, but we know from the regional seismicity that the seismogenic thickness is deeper than that. This means that there leaves the lower half of the site of this region. It's a potential for future earthquakes. That is one possibility that we can derive from combining and looking at all of these depth information. The last information or some key observations that I like to share with you today is, again, back to the title, where how can we apply InSAR to look at some of these hidden faults and what are the hidden seismic hazards in this region. So I'm showing this regional map. I'm stepping out a little bit. So Sayabuli earthquake is on the corner where my mouse is right now. But in addition to the Sayabuli earthquake, in these relocated earthquakes are now plotted in year of the event. So we relocated 158 earthquakes from most of them are from 2007 to 2023. And we found that there are around 5 important greater than magnitude 5.5 events. So the foreshock of the Sayabuli earthquake, the main shock itself, the aftershock, and the 2 Sheungtung earthquake. Now let's see if we can actually apply this InSAR to characterize some of the earthquakes that have lower magnitudes than the 6.2 main shock. And when we look at this map, at first glance, we would think that a lot of the earthquakes or the Sheungtung earthquake tends to happen on a northeast trending fault because it's so pronounced in the topography. Again, the Sayabuli aftershock as well is one of the signals that we were very lucky to actually be able to get an InSAR signal from an earthquake with a magnitude 5.5. So maybe I'll share with you in the room that there are some criteria of InSAR. For example, with a global study, a magnitude 5.5 is around the threshold that you can see InSAR signal, and around 10-kilometer depth is around the threshold that InSAR can produce the signals of earthquakes. So 5.5 and around 10-kilometer, but that also varies, but that's the average. So this, we were really lucky with a 5.5. The left-hand side is the data, and the second column is the model. So we also did a northwest trending fault, and we modeled a northeast trending fault. But because of the descending intergram has a very clear lobe shape, we will be able to actually confidently say that the northwest trending fault is the causative fault plane and not the other one. The other earthquake we tried to look at is the Sheungtung earthquake in 2022. This one is a lot more challenging, and it's well known in Southeast Asia that the vegetation, the humidity in the air, in the atmosphere contributes to these signals being decorrelated or very noisy. We also made a northwest trending model and a northeast trending model fault. And because of these lobes in the data and these more narrower lobes and a more broader lobe in this region gives us the observation to confirm that the northwest trending fault is the causative fault for the Sheungtung earthquake. So from this study, we found that there is at least 3 new faults that has not been mapped before. And what this means for Thailand is, or for our neighboring countries, that with the tools of InSAR, we know that these 3 new faults exist. And if there are future dams or reservoirs or any schools or hospital or high importance buildings that is going to be built, we can use the information of these faults as a starting point of what we can analyze for like structural analysis for buildings, for example. And because these faults are short in 10 to 20 kilometer scale in relation to Diem and Phu fault, for example, and that's 100-kilometer scale, these shorter faults should not be overlooked in seismic hazard models in this region. The other takeaway point is we learned that these hidden faults, earthquakes on these hidden faults have some common rupture behaviors. One of it is high shallow slip deficit, and the other is highly distributed aftershocks away from the main fault zone. And what this means for the local government is that when we know these behaviors, we can expect ground shaking maybe in a broader region, and that is something we can communicate to first responders that go out in the field. Or even for scientists or geologists that we want to collect perishable data that is away from the fault zone. So when we conduct field work, we know that we need to walk a little bit broader because this is a fault, earthquake that ruptured an immature fault. And the last takeaway is that personally, I think that each utilizing different methods, utilizing the strength of different methods is a very powerful thing to do. So with InSAR, we were able to identify the buried fault. We were able to know where the peak slip is. With seismology, we know where the earthquake started. So with the combination of this, not only we get the along strike hazard, meaning we know that it might be a simple fault trace, it might not be a fault jumping. There is no segmented, but along depth, when we look at the along depth profile, we know that there might be some hazard, like the lower half of the seismogenic thickness might rupture in the future. So that is one of the observations we can get from combining different methods together. And to conclude my presentation, for those who are interested in resources, some publicly available resources, a lot of times I go into Comet Lixar website a lot. It's a portal run by the group in the UK. And if there are large earthquakes, there are pre-processed earthquake infograms that they upload in this website. So I recommend if you're interested in earthquake infograms, they also have volcanoes and other data too. You can go in this portal. If you're interested in relocated earthquakes around the world using similar methods as this study, you can go in the global catalog of calibrated earthquake locations. And as of right now, I've received a lot of help from DMR, from TMD, กรมอุตุนะคะ for the data for this research, and the relocated events for the Melao earthquake in Chiang Rai is already uploaded in GCell. The InSAR lookbook, we've submitted the manuscript to Seismica, and the study I presented about Sayabuli earthquake is already submitted to Geophysical Journal International. And when this paper comes out, the information will be publicly available at GCell as well. If you want to download, it has all the KMZ files that you can open up in Google Earth to view the earthquake locations. And this work is not possible at all with all of my collaborators, my PhD committees, my research group in University of Victoria in Canada, and as well as the Melbourne Earthquake Science Group in Melbourne, Australia, and scholarships I receive as a support from this research. And all the faults information and the waveforms that made this study possible. Maybe you in this room don't know, but I've received a lot of help from DMR and TMD throughout the 5 years of my PhD, and I'm really appreciative of that. And just to conclude, I met Hishat and Hitsuit back in 2018 in a trench excavation in Myanmar. And that's how our story began, getting very hyped and excited about paleoseismology. So I really appreciate the support from everyone here. And these are my research group in Canada and Australia. ขอบคุณค่ะ
Thank you, Dr. Sethanant, for your presentation, and also thank you for your practical you gave us that make my brain sail a lot and make me fully wake up in this morning. And now the stage is open for all questions and sharing experience. Or for the first message in the chat from Zoom is the case study of the earthquake in the Sayaburi province is very interesting. Are you still continue study or monitoring?
Oh, that's a great question. I think I always get excited every time there's an earthquake in Thailand, which is my home country. Right now, the study is wrapped up in the manuscript, but I think recently there was an earthquake north of where the boundary of my study area is, and my collaborator Eric Bergman, if I go back, Eric Bergman is the collaborator in Colorado, United States, who lead the earthquake relocation method. He is also intrigued to incorporate the recent events north of Tung into the cluster as well. So if there's any update, I'm sure it will be uploaded in GCell. Thanks.
Thank you.
So the other question, do changes in vegetation or infrastructure after an earthquake affect InSAR's ability to track ground deformation? If so, how do these changes the impact results? To address that, yes, it does. The vegetation and infrastructure, when it changes between the before and after image of the earthquake, it produces a lot of noise and patches that we have to mask out. So if the infrastructure and vegetation is not, the region is not broad enough, it will not significantly affect the fault geometry because the deformation field of the earthquake is in kilometers and tens kilometers of scale. So when we project that displacement field to the subsurface to get the fault, those dots on the surface does not affect the fault geometry, but it affects the SIP distribution model because if the vegetation and infrastructure doesn't allow us to get the information near the fault, then the amount of slip will change. It might change like 10 centimeters or so. Oh, could I share my presentation? Yes, of course. There is a bit of a process for making sure with my co-authors that they are okay to share these images because it's in the process of publication. But I'll make a draft of what is shareable and I will send to DMR.
Thank you. And what is the minimal earthquake magnitude that can be detected using InSAR analysis data in the case of a normal and slightly fault earthquake?
Yeah, so not a rule of thumb, but on average is around 5.5. And there's a combination of what to consider. It's the size of the earthquake and the depth of where it occurs. So on average, it's the same with different types of earthquake, whether or not it's normal or strike slip. It's around 5.5 magnitude and around 10-kilometer depth is the maximum threshold. However, in the case for Australia, which is where I'm working now, there are a lot of earthquakes in the scale of 4.9 or 5.2, but it's really shallow. It's around 5-kilometer depth. So if the earthquake is shallow, even though it has a lower magnitude, it is still detectable with InSAR.
And talking about that, most of the cases in Thailand, I think, they have a very low magnitude of earthquake. And I'm wondering, is there any study I mean, even the earthquake is very small, but then according to the tectonic theory or something about Thailand, it's been a long development of tectonic activities. So is there any possibility of using InSAR to map the terrain deformation for a long period of time and matching with a series of small number of earthquakes? Can we still apply the InSAR to study the fault system? I mean, of
Yeah.
course, in general, as you already mentioned, you only say like it might run from M4.5 to 50 for a very shallow
Yep.
kind of earthquake to be able to use InSAR.
Mhm.
But then again, plus time,
Yes, that's a great question.
okay? If you're considering the time spanning
Mhm.
of the fault development,
Mhm.
can we still use InSAR to study? If this is the case, and if this is possible,
Mhm.
and that would be very good for Thailand to
Yeah.
start looking into using the InSAR for the fall application, right?
Yes, that's totally great recommendation. There is a field in InSAR called InSAR time series. You might have heard. So this is earthquake interferogram. So you get the shortest time available before and after an earthquake. But in a tectonic scale, if you're interested in how the faults are accumulating strain, a lot of research group does InSAR time series where you get a lot of stacking of the SAR images from time from so the ones that are available, the freely available InSAR data, SAR images is the Sentinel one, and they launched in 2014. That's why we don't have signals for Melau earthquake because the satellite launch after Melau earthquake happened. But if we use ALOS or other satellites or Landsat, it goes back to 1990s. And if we have the capabilities and the people here, we can do a lot of the InSAR time series, and maybe Metanfall could be an interesting one to look at because I think the recurrence are we due? And we can look at how the strain is accumulated. Mhm.
So, okay, are we going to write another project proposal?
Yes, and it is a question from the meeting room from Miss Kun Savitri, please.
Thank you for your fascination presentation, and also it's thank you for share your knowledge for us. I think that's one is a good a good way for a initial to think and develop in the DMR, and also including in the Thailand like this. And I would like to exchange about in your knowledge. I would like to know about uh inter and also post interseismic and post seismic time series in the when we using the time series inside to detect in the hidden fault.
Yes.
Yeah. Do you have how to or for example the method to to predict or to find the hidden fault in the Southeast Asia? Because do you know that in Southeast Asia we have limitations about forest area zone, and also we gonna a lot of a higher T, and also that's why the sentinel it's like a C band, it cannot more deep than
Mhm.
to surface.
Mhm.
Yeah, and also yeah, I would like to know this. You have
Yeah, so processing the intergrams for Sayabuli is really difficult. And I received a lot of help from my supervisor and a lot of postdoc in the group when I was there. In the code that I use, there are lines that you can adjust about the masking of the noise of the interferograms. The one that I work is co-seismic, yeah. But there are, my colleagues does post-seismic InSAR time series, and another of the visiting student at my group at the University of Victoria specifically write codes to tackle the problem of the vapor in the air. Like, how can we create a more coherent interferogram in China and in Southeast Asia? So I can send you their contact and papers, because that's out of my expertise, but I can facilitate those connections.
Thank you so much.
And there are lots of questions about the vegetation area in the Zoom chat. For the first question was product of SAR images. Did you analyze? If it is Sentinel-1 C-band, is it possible to have scatter noise from the vegetated area if you have done with the L-band and X-band? Are they not affected by noise from vegetated area?
Yeah, so the product, thanks for the question. The product that I use is the Sentinel-1 C-band, and that's a higher frequency. There are the L-band and X-band available, but I think like for the purpose of the earthquake studies, that's why I chose the C-band to do the study. And there was a lot of the process of masking out those areas like manually instead to be able to get the interferograms that is statistically has a lower root mean square fit. But that's a great suggestion. I'm probably gonna keep that in mind in the next time to explore the L band and X band more.
Thank you for the question from Kun Sasin. And the next one is from Kun Kunlasha. Thank you for your presentation. And the question is, I would like to know more detail about how many images you use to detect this fault and which software you use to overcome and the vegetation area and atmospheric effects. Do you have any ideas for suggestion to overcome the vegetation area?
So thanks for the question. The software that I use is Gamma, GAMMA, and in those codes, there are the lines in the code that you can play around with the threshold that you want to mask out the like the coherence of the image. But again, with the Sayabuli earthquake, I think we were very lucky that the SAR images that we got has good enough coherence to produce an interferogram. And the earthquake was large enough that it kind of overcome the vegetation effect. Because if you remember from the slide I show of the Shengtung earthquake, it was very, very noisy, very decorrelated. And that's a combination of vegetation, lower magnitude earthquake, that the signal wasn't strong enough to be able to get that coherence fringes. So it's really challenging in Southeast Asia about the vegetation. And I think I'll maybe send the paper about the vapor effect and the vegetation effect to DMR or PM as well, so that it can be shared around. And the other thing that we tried for the interferograms is we used the GACOS model. And the GACOS model is also, I can type it here, is the model, a global like vapor model that you can subtract out from the InSAR. So this is also something we applied for the interferograms. I hope that answered the question.
Yes. For the question from Kun Saga, I think Dr. Sethanant is already answered for your question. The question from Kun Sakda is, could you please give DMR people more detail about how to access fault displacement or slip distance
Um, I'm not sure. Can you explain a bit more what that means, please? To assess. ใจว่าแปลว่าอืม fault ขึ้นค่ะ how to assess displacement oh the offsets โอ้โอเค ได้ค่ะ ได้ค่ะเดี๋ยวขออนุญาตกลับไปอันนี้นะคะ so oh I don't have the scale ขออนุญาตกลับไปอันนี้เลย so for Sentinel-1 interferograms from blue to yellow to red is around 2.8 centimeters. I'm going to approximate and say 3 centimeters. If I go back some more. So I forgot to mention one full cycle of the rainbow color is 2.8 centimeter for Sentinel-1. So what that means when we see a real world interferogram is if you interpret that the fault is here, this is one cycle. So let's count the number of fringes together. So this one fringe, 2, 3, 4, 5, 6, 7, and it goes very detailed. So for example, if I say I can count 10 fringes or 10 cycles of blue, yellow, red, it means 10 times 2.8. So that is 28 centimeter of displacement on the ground. And I also count on the north. So one cycle, 2, 3, 4, 5, 6, probably 15 or 20, but let's say another 10. So the northern side moves 28 centimeter. And that's how we read the fringes in an interferogram. This is a bit easy because it's a butterfly shape. When we go to Sayabuli, it's a bit difficult because we have 4 lobes, but let's say we're going to use the descending interferogram as an example. How many cycles of the rainbow colors we see? So 1, 2, 3, and now we lose the signal. So in this case, I am confident to say there is at least 10 centimeter of surface displacement on the east side. And I'm confident to say, maybe I see 2 fringes here. I'm confident to say there's around 5 to 6 centimeter of displacement on the west side.
Thank you, Dr. Sethanant. Is there any question or comment? Okay, Sakti, please.
That's okay. I would like to ask you about if in the DMR we gonna make the project, but we didn't have like a facility like a software or something like that. Could you please recommend like a suitable and also like a good for our department? Yeah, it's like also including commercial and also like a free open source or something
Yeah.
like that.
The other open source I know is GMT-SAR. Did you use that? And ICE. I don't know about STEM, but I know GMT-SAR and ICE. Those are the two like the GMT-SAR is, I think it's publicly available, but I think it might be a bit of a black box where you cannot see a lot of the codes, so you might not know what's going on. But for the atmospheric correction, GACOS is publicly available.
And also some people is like we are like geologists, we didn't a lot much about like programming. It's that's why we could you repeat like a recommend is like a easy software to like a process is that like a know about is the like how to do in this bottom, it's we gonna just click the bottom
Yeah.
or something like that.
Yeah. The gamma that I use, it's commercial, and it's a bit difficult, and I got a lot of help from my colleague. The one that I recommend might be GMT-SAR, but this is the one I know. There might be a lot more software that I don't know, but there is a workshop. I can type here, Gauge Sage. So this is a workshop mostly run in the United States. I attend this workshop online one time, and they teach you all the processes for doing GMT-SAR. And I think if it's really helpful because it's a hands-on experience, and they would guide you through downloading, like what website you have to go to download a Sentinel-1 data. So that workshop is like a multi-day workshop, and you have to download the data by yourself and like really hands-on. So I would recommend people who want to learn how to process InSAR to register for this workshop. I think they do it once a year around June, July. Snap.
There's a question from Kun Sasin. Can you approach analyze through Snap?
I'm not, I don't know what Snap is. I'm not sure what Snap is. This เป็นอะไรบ้าง? Oh, for InSAR? Okay.
Yeah. In my opinion, and also I can like process interseismic with the snap. It can, but you also like including like Ubuntu also, because it's some like to unlock in the data is like should be both for snap and Ubuntu. Yeah, we can process it. Yeah.
Thank you,
Yes,
Kun
thank
Sasin,
you.
for your explanation.
Yes, thank you. I understand.
It's my turn. Thank you, Grace, for excellent and interesting
ขอบ
presentation.
คุณค่ะ
ครับ so again, thank for confirm the what I interpret the source of the earthquake northwest trending faults generated the earthquake 6.6 2019. This is look at that. You know, at that time we doubt which fault
Yeah.
generate the earthquake, the Dien Bien Phu fault, not east trending fault or conjugate fault.
ค่ะ
At that time, I say it should be the northwest trending fault. So can you show me the location, exactly location of the fault that you interpret on the map? There's what is the SYBF fault? Or
Oh, Sayaburi fault zone ค่ะ So I think I looked at a lot of literature, other mapped faults, and I found that some พี่อาจารย์เหมียวพี่มหิดล like I think they withอาจารย์the project อาจารย์ปัญญา is on as well. They did some trenching, like 11 trenches actually in the Sayaburi fault
okay.
zone. So that's why I labeled this as Sayaburi fault. And that's
Yeah. Where is the Nan area? Seems to be 6.2 earthquake magnitude. It's close to Nan area. Is this? This is the same event or?
same ค่ะ
But your fault is far away from Nan area.
So the country border is a dashed line. It's a bit difficult to see, but
Oh, I see. Okay. I mistake. Okay, I see. And then you map the faults in red line. Is this
the red line is the InSAR,
2021 earthquake event? Or
the shorter one.
Okay, so you mean the blue, the
So this one is the aftershock.
okay,
The shorter
aftershock and the
one.
main shock faults.
The main shock is a longer one. So it's doing an oblique angle.
So did you check the geomorphology around the fault zone?
Yeah, that is something that we didn't look into a lot.
You,
that-
okay, I
Mhm.
understand. You know, we at that time 2019 earthquake event, we interpret the back drive more left. Should be the source of the earthquake. Okay, so I wonder if should be great if you recheck the geomorphology along the red line.
Yeah.
Do you have geomorphology
Yeah.
indicated the active fault, something like
That's
that?
a good advice. Yeah.
But I agree with you. The northwest south, northwest trending fault generate the earthquake at that time.
I think the challenging thing about in this case is this is a fault
I
that
don't
had-
doubt. I don't doubt
yeah,
how the
yeah.
InSAR technique
Yeah.
is insist consistency with my interpretation. But the
Yeah.
location of the faults, I think the fault should be moved more left.
I see.
Morphology at the present, I think it's impossible. So in that case, I think that you may be right in the case for the SAR.
Yes.
It's impossible. You need large earthquake to show or to give us some evidence for geomorphology. So geomorphology cannot be applied as a kind of supporting evidence for the SAR. I don't think in order to do that, I'm afraid.
I agree. Just wonder about the exact location of the fault that you interpret on the map with right.
If there's any, yeah.
Mountain, high
Mhm.
mountain.
Do you check with the focal mechanism? And then it has a kind of auxiliary and the through things. And in this case, it's probably the auxiliary. I don't know. I just want to make sure this is all right.
I just want to make sure that I understand it. According to your map over there, the red lines, is that the red line you draw it from InSAR study?
Yes.
And the focal mechanism is just something that is deeper. So that indicating that the red lines are at the surface.
Projected to the surface, yes.
Projected to the surface. So it's supposed to be over the focal mechanism, right? If you talk about projecting the epicenter, for example.
Yes, it's dipping to the southwest.
Or is it indicating the dipping? You have to explain that. I mean, we are talking about two different location now. If you talk about the surface, and if the fault plane is more or less not vertical, right? It's dipping somehow. So the focal mechanism should reflect something that shift from the surface, rupture. So if you insist that this is the projection of the focal mechanism up to the surface, then it has to be exactly on the same location, right? Are you with me?
I don't think it has to be the same location.
No?
Because the InSAR gives us where the fault is, but the focal mechanism gives us where the peak, the slip is concentrated. So it gives information of depth, but the InSAR gives location of the fault geometry.
Okay, it can be different.
It can be different.
Okay. But there must be some rules. I mean, it cannot totally different. I mean,
It
I don't
might
know, I
be
I
like
may
the
be
same
wrong. I
zone.
mean, sorry.
No. I think that's a valid point. A lot of times the focal where the slip is concentrated, it's around the main slip plane of the InSAR. Yeah. So yeah. Yes. The focal depth.
It's going to be, it's possible to use SAR.
Yeah.
In China, I guess that many geoscientists at present they are trying to work on earthquake prediction using SAR. Have you heard that?
No, can you tell me about it?
I
please?
don't know about, but some of my friends told me about something like this, but it's very interesting because if in that case, you may, this is a good, your presentation is quite good, but maybe a little bit difficult to use in Thailand because Thai earthquake is not only small but also
Noisy.
something like that. I don't want to say that.
Okay, and I think time is right now. Thank you everyone for all questions and comments. May I invite Dr. Titi? May I invite Dr. Titi to give a token of appreciation to our speakers? Dr. Titi, please. Sorry for my interrupt. The first one for Dr. Israporn Sethanant. Thank you. And the next one for Kun Nattaphan Bangpa. Thank you, everyone. Ladies and gentlemen, we are going to the end of today's special talk. I hope to see you again in the next talk. Thank you very much for your attention. And it is my pleasure to be your MC today. เป็นเกียรติอย่างยิ่งค่ะที่ได้รับหน้าที่พิธีกรในวันนี้ในนามของกรมทรัพยากรธรณีกองอนุรักษ์และจัดการทรัพยากรธรณีขอขอบคุณทุกท่านอีกครั้งค่ะ and enjoy your lunch. Thank you.